everybody! Today we're going to talk about solution sets to ax equals b. Last time we talked about how to formulate systems of linear equations into this nice compact matrix equation form that we're going to call ax equals b. And so when we say we're going to talk about solution sets to ax equals b, we're still talking about solving systems of linear equations. But what we want to do is we want a better way to describe all possible solutions in the term of the x vector. Recall that we know ax equals b has no solution, a unique solution, or infinitely many solutions. And we know this because we know things about the corresponding augmented matrix, this guy. Based on his pivot points, we know things about ax equals b. So before we jump off into deep water, we're going to start with a simple case, and it actually has a name. We're going to talk about homogeneous linear systems, and this is a fancy way of saying we just want b to be 0. So ax equals 0 instead of having numbers on the right-hand side. Cool fact about this always has a solution, because if you take a times 0, you're going to get 0. Something times 0 is 0. That was one of our matrix vector multiplication properties that we had in a previous lesson too. We don't really care that much about this though. We call it the trivial solution. 0 is not very interesting. So then the question arises, when is ax equals 0 going to have an interesting solution? So let's review the 3 possible outcomes for ax equals 0. It could have no solution. What does that mean? It means no pivots, or it means there is a pivot. Pivot in the last column. So let's review what that would mean for ax equals 0. In this particular case, our augmented matrix will look like a1 up to an, so all of our a columns, and then we're not going to have a b over here, we're going to have 0. So in order to find the pivots, we have to put it into row echelon form. So you're going to do some row operations, you're going to multiply by scalars, of scalar times 0 is 0. You're going to add rows together, which that means the right column is going to get added together. You're going to still get 0. So this guy will always be 0. Very dramatic pause to say that. So if it's always 0, what does that mean about pivots? It means we can't have pivots here. Pivots mean non-zero numbers. That means we cannot possibly have the case where we have no solution, which matches the information that I just told you before about if we're guaranteed at least one solution. Okay, next case, the unique solution. Well, if we have the unique solution, that means we have no free variables. We have no free variables, that means our answers are locked in. Remember, you can't be like, oh, well, x1 equals something in terms of x3, and x3 can be anything. None of that. You get a set of numbers that go together, and that's it. That's the only choice. We already know the unique solution. I already told you, x equals 0 is always going to be one of the solutions. So we know it. It's x equals 0. And then we have infinitely many solutions. How do we have infinitely many solutions? When we do have free variables. So this is the only time interesting things happen. Okay, We even have a lemma saying exactly that. Ax equals 0 has a non-trivial solution if and only if the system has at least one free variable. So let's go ahead and move on to our first example. We have Ax equals 0 is our format, which means the only information I need to give you, because we have B, it's 0. X is variables. I just need to know what A is, and I can move forward trying to solve this. So we have A. We have it's 1, -5, 3, -2, 7, 3, 4, -14, and 6. And we can try and solve this equation, assuming it has a solution. And if we find the solution, we're going to find the space of solutions. So instead of writing the coefficient matrix, I'm going to write down the augmented matrix just to be careful, because we know that B is a bunch of zeros, so you just put zeros on the right-hand side, and they're not going to do anything particularly interesting. Okay, so first thing I want to do is I'm going to try and get these guys to all be 0. I want my staircase. So that means this 2, he's standing in my way, and he's got to go. So the way we're going to do that is we're going to modify row 2 by adding 2 times row 1. So row 1 stays the same because he's doing the modifying. Row 2 is going to change, so we're going to do 0, and then that's going to be a -3, 6, and 0. Yeah, cool. Then you'll notice I didn't write row 3 down. It's because I'm being lazy. I'm going to modify row 3 now as well, because I'm going to use row 1 to do that. We're going to say, I also want to remove him. Same time. I can spell remove, that's a thing. There we go. So this time, we're going to modify row 3 with row 1. -4, row 1. So that's going to be a 4 minus 4, which is 0. 14 plus 20, 6. And then this is -18. Yes. But only if I copy the problem right. Okay. So now, next thing to go is going to be this guy. And I think it's pretty easy to see that we have, I'm going to scoot him over a bit. We have to multiply row 2 by a 2, and that will completely eliminate row 3. There we go. Okay, so this is row echelon form. You may stop here. I don't wanna. I'm gonna keep going. This next step is gonna be a step that I haven't shown you, but remember we are allowed 3 row operations. And I think the first one I listed was multiplying by a scalar. It was either the first or the second one that I said was multiplying by a scalar. And that's what I'm going to do now, because this row right here has a -3 where I would like to have a 1. So I'm going to make it have a 1. There we go. Row 1 stays the same. Row 3 stays the same. Row 2 gets modified. This is wrong. I've made a mistake, haven't I? Sorry, I messed up on my very first one. This guy right here, I had a 6 plus 3, not just a 6. So I've fixed it in pink. Okay, so then we have one more row operation, and we could get this into reduced row echelon form if we get rid of this -5, because remember, reduced row echelon form means that you have your pivot has zeros above it as well as below it. So let's go ahead and remove this 5. We're going to do row 1 is getting modified by row 2. I'm going to add 5 times row 2. So row 1 is the one being modified, so I will write him last. This is going to be a 0. This is going to be a -12. Excellent. Okay. So now that I have reduced row echelon form, I am going to convert it back over to the system of equations to try and figure out what kind of solutions I even have. I guess I should point out that these guys have pivots, so then x1 and x2 are going to be basic. Ooh, that was too much. And x3 is going to be our free variable because we have no pivots here. So no pivots equals free. So then translating this back to a system of equations, we get x1 minus 12x3 equals 0, x2 minus 3x3 equals 0. We have x3 is free. And I need a little bit more space. There we go. So now that I have x1, x2, and x3 equations, I'm going to take this a step further, and I need to solve for my basic variables in terms of the free variables. That means x1 is basic, so it's going to equal something involving x3 because x3 is the free one. Same thing for x2. And now I am ready to write my x vector, which is going to be my solution vector. So x equals, I'll be really careful at first. It is x1, x2, x3. But I know what x1 is. It's 12x3. And I know what x2 is 3x3. And then x3 was free, so he's just his lovely self. I can factor x3 out of this, and we are left with this vector here. Does this look like something? Maybe a linear combination? Because we've got a constant that can be anything times a vector. Hopefully you can see that, because that's what it is. And what do we want to think of when we think linear combinations? I'm fostering 2 kittens. Ignore the background sounds as they fight. Landon. So linear combinations means span, which means we can write this solution using span. What is the span? Oops. What is the span of one vector? It's something I've already talked about. You remember it's a line, maybe? We had some cool graphs. So it is the line through the origin in the direction 12, 3, 1. I think I phrased it including the vector 12, 3, 1 last time, would match my phraseology from last time. Cool, so we were able to describe the solutions to this matrix equation using span and what we learned about it a couple of lectures ago. So let's try another example. We're going to use a different matrix for A now. Same deal though, we copy it down and we want it to be in augmented matrix form, even though we know the right hand side is going to do nothing, just to be consistent. And we are going to reduce it. We're going to remove that 2 right there. So we're going to do row 2 minus 2 times row 1. 1, 3, 0, negative 4, because row 1 stays the same. Row 2 is now all zeros, which means we have a lot of free variables. The only pivot is right there. So x1 is our basic variable, while all the other ones are free. So x2, x3, x4 are free. And we have an equation for x1 involving x2 and x4. And we're going to solve for x1. Okay, so there we go. We have x1 and all the rest are free, which means we are now ready to do our solution vector x. So we said x1 is negative 3x2 plus 4x4. And then we have x2, x3, x4 are free. And I'm going to use properties of vectors to kind of split this apart and organize it. Like I kind of want to put the x2s by themselves and the x3 by itself. So let's get organizing. So x2 has 2 places it shows up. It shows up in the first entry and the second entry. So our first vector just has x2's in it. And then if we add it to this vector, we'll get that x3 taken care of. And now all we have is the x4s, which show up in the very first and last entries. All right, and I'm going to take this another step. I am going to factor out my x's. Okay. And then what can we say about this? It looks very linear combination-y again. We have vectors times numbers. And since it's a linear combination, we can say that it is span of the 3 vectors in question. And then I am sorry, I do not have cool visualizations for this because I draw the line at drawing pictures at 3 dimensions. All right. And then I did want to make a note about this form right here, which matches this form right here. So the linear combination looking thing. It has a special name. It's called parametric vector form. And solutions of this form are called parametric vector form because the free variables are thought as parameters. And that's just mostly so that, again, you know what I'm talking about, so that I could ask you to formulate your answer in terms of span or leave it in parametric vector form. Okay, so now we're going to move on. We want to know, what about if b isn't 0 anymore? How does that change things? And I think that's very nicely illustrated if we go back to example 1 and we use that matrix. So that is our matrix from example 1. But now, here on the right-hand side, we don't just have zeros anymore. Things got interesting. Now let's go ahead and solve this out. We're going to write our augmented matrix. 1, -5, 3, 2. -2, 7, 3, -1. 4, -14, -6, -14. Okay, so now we're going to solve it. First thing we're going to do is we're going to remove this 2. We're going to remove the 2 by doing row 2 plus 2 row 1. So let's go ahead and do that. And then row 1 stays the same. 2, row 2 changes. Let's see, it's -3, 6, 3. And then I'm going to do the same thing I did before and be lazy. I'm going to get rid of 4 using the operation row 3 minus 4 row 1. And the result is 0, 6, -18. Oh my goodness. I just keep writing 6 right there. Okay, it's a 9. I promise it's a 9. There we go. Okay, and then just like before, we are going to reduce this again. Row 3 plus 2 row 2. So 1, -5, 3, 2, because row 1 stays the same. 0, -3, 9, 3, 0, 0, 0, and 0. So that means we are still in the land of interesting solutions because we have a free variable. And then, just like last time, you may stop here. This is row echelon form. I think it is a good idea to keep going. So I will. We're going to multiply row 2 by a -1/3. So row 1 stays the same. Row 2 changes, but row 3 does not. It is still all zeros. This is going to be 1, 3, -1. Yes. And then very last row operation is row 1 plus 5 times row 2. So if you didn't notice already, go back and compare. I used the exact same operations to reduce our matrix as I did in example 1. Every single one of them was the same. And in fact, you'll notice the right-hand side of our matrix is the same. Which makes sense because we started with the same numbers, we did the same operations, and we got the same matrix. So that means we're doing things right. But now that we are here, I'm going to write things in their equation form. So notice this guy means x3 is free because we have no pivot. And I'm going to flip the page for this. So we've got x1 minus 12x3 was equal to -3. And then we've got x2 minus 3x3 was equal to -1. x3 was free. And then we solve for the basic variables in terms of our free variable. So x1 equals -3 plus 12x3. x2 equals -1 plus 3x3. x3 is free. Okay, let's put this in vector form. So this is going to be -3 plus 12x3, -1 plus 3x3, and x3. Then I want to organize this vector into two separate vectors, one with x3s and one without. So the one without looks like -3, -1, 0, and then plus 12x3, 3x3, and then 1. I'm just going to go ahead and do that in this step. Pull the x3 out. Okay. What does this look like? It looks like example 1's solution, hopefully, because it is. And that's not a coincidence. All right. So in general, non-homogeneous problems are going to have, right here following along with the words, non-homogeneous problems have solutions that look like the solution belonging to their homogeneous counterpart plus another vector. So let's go back just to have a picture of that. So here's our homogeneous solution plus another vector. And then this other vector has a name. It's called the particular solution. Okay. So the big picture is, if you have a non-homogeneous problem, the solution is going to be the homogeneous problem solution plus a vector that's like locked in stone. It doesn't have any variables. See, this one has no variables multiplied with him. It's called the, I'll go ahead and label it here for you guys. This is the particular solution. And it's called the particular solution because he solves the equation all on his own. If we got rid of him and we did not plug this guy back into our solution, the particular solution would be okay. Why is that? This guy contributes nothing. He solved the homogeneous equation. That means when you plug it in, you get 0. So I'm going to do this note in a different color. Plug him in and you'll get the 0 vector because he solved the homogeneous problem. So basically, we have the portion that actually solves our problem plus the portion that's going to just add 0. So the real portion that's going to give us the right-hand side plus something that ends up contributing nothing in the end. But this is the most general way to write our solution, and that's why we write it this way. And so here's our theorem that says basically everything that I just said. We have AX equals B is consistent with some particular solution VP. Then the space of solutions for this guy is going to be given by vectors of the form particular solution plus homogeneous solution. and it's always going to work like that. In fact, we're going to prove it real quick because it's very straightforward. We want to show AX, or no, you want to show X equals V particular plus V homogeneous solves AX equals B. Okay. And it's literally just as easy as plugging it in. So you have AX, but we know what X is. X is VP plus VH. And then we have matrix vector multiplication properties that are going to allow us to distribute. So here we go, we've distributed. And then we know what A times VH is. It's 0. How do I know that? VH is the solution to the homogeneous equation. So this means, right here, the thing that I've highlighted, if you plug in VH right here, you're going to get A times VH equals 0. So that's how I know that's a 0 right there. And then we also know what A times VP is. What is A times VP? It's B. And that's from the first part up here. We said AB is a consistent system, which if you forgot what consistent system means, it just means that it has a solution. And then I told you, it has the solution VP. So that means you plug VP into AX equals B, and you're going to get A times VP equals B. So then we just have B plus 0, which is equal to B. So yes, if you take the particular solution and then you add on the homogeneous component, or the solution from the associated homogeneous system, you're going to get a solution for the non-homogeneous problem. Okay, and then that's all I've got for right now. We were able to classify some solutions for AX equals B by using parametric form, and then we found out something really cool about what we can expect from a non-homogeneous system. It's actually very closely related to the homogeneous form. Okay, and that's all for now. Thanks, guys.